In this lesson, we're going to look at vectors in a plane. When we're working in applications of mathematics, a lot of times we can represent things with values using a single number. However, sometimes we need to represent a quantity that has multiple values. And so we're going to use something called a vector. When we have a number that can be represented with a single value, we call that a scalar. So a scalar, we're really used to scalars. They're just plain old numbers, nothing too fancy about that. When we have a value that needs multiple quantities, we call that a vector. A vector is something that has a quantity that has direction and magnitude. All right? So, and lots of things like velocity and acceleration and even temperature. A lot of physical quantities can be represented as vectors. So we have direction and magnitude, and when we look at vectors graphically, we're going to represent them as a directed line segment that has a certain length and a certain direction. Okay, and the key here is that the length is the magnitude. All right, so the length is the magnitude, so that's going to be an important thing to know. All right, and so we're going to need to find that length. We're going to need to find the direction. That's where some trigonometry is going to come into play here. So now we have, for example, here we have two vectors. The first vector is graphed from 0, 0 here at P, and it's going out here to Q at 5, 2. Call that PQ. Notice we've got the little ray over the top. A lot of times this is our vector symbol. It's not exactly a complete arrow, but a half arrow. We write the magnitude as the absolute value of PQ. Okay? So that absolute value tells us how long it is what we want to know. Some key features here is called the initial point. That's where the vector starts. And we have the terminal point, and that's where it ends. All right. The initial point is always a dot, and where the vector ends, the terminal point, that's always going to be an arrow. All right. So initial point, terminal point, initial point, terminal point. Okay. When we have standard position, we have that means we have an initial point at 0, 0, okay, at the origin. So when the initial point is at the origin, we call that a, well, let's see if we can spell. We have initial point at the 0, 0, all right? So this one is in standard position, this one's not. Now notice the length of these two vectors is the same. So they have the same length, and notice they're going in the same direction. They got the same angle. So these two vectors are called equivalent vectors, and because they got the same direction and the same magnitude, they are equivalent. All right. However, they're not the same vectors exactly because they're one of them is in standard position, and a lot of times that's more useful. All right. So describe vectors in standard position, such as vector V, which is PQ. Now notice this is a bold, small v. A lot of times we'll use that for naming a vector. We have a terminal point of 5, 2. Since it's in standard position, we have what we call component form. Component form just means we're going to write just the terminal point, 5, 2, and we're going to use these little pointy brackets like this. Okay, these little sharp brackets. So that's going to tell us that we're talking about a vector here. It's not. We're not just talking about a 0.52. It's a vector. So, for example, if we have the vector -3, 2, that means we find the point -3, +2 up here, and we're going to have an arrow going from there. Actually, let me try it this way. So we have. Okay, so let's get it all the way there. Okay, doesn't want to go all the way there. There we go. All right, then we have the vector 3, -2. That's going to go down here, and that's going to give us this vector right here. Okay, now these are what we call opposite vectors because they both start at the origin, they're going in exactly opposite directions, and they're the same length. All right? Now, next thing we want to consider is this. What if we have these points here? This point right here is 2, -4. And this point right here is 7, -2. And we want to figure out, without actually just counting, we want to figure out what this is equivalent to in standard position. Well, we notice that since we're going from 5 over here, we're going from 7 to 2, well, that's a distance of 5. So if we have a distance of 5, then we can find that just by subtracting. So 7 minus 2 gives us 5. And that's our 5 right here. And then if we have, we're over here at, up at -2 is our y coordinates. This y value is down at -4. So what's that rise? Well, that rise there is going to be -2 minus -4. Okay, so -2 minus -4. That's going to tell us we're going 2 because it's going up 2. All right, so we're going up 2 over 5, and that's what gave us this right here, where it's going up 2 and over 5. Okay, so this is the vector 2, 5. Okay, so we've got the vector, I'm sorry, I'm changing it around, we've got 5, 2, because we're going right 5, up 2. Okay, so if we subtract the coordinates, we get that rise and that run. Okay, and to find the magnitude, well, we just got a Pythagorean theorem here. This is 2, this is 5. We're really finding the distance between these 2 points. The magnitude is a distance, so we're going to use the distance formula to find the magnitude. So we can say the magnitude of this vector v is just the distance formula, which is a square root of 7 minus 2 squared plus -2 minus -4 squared. Okay, and all that's going to give us is 2 squared plus 5 squared, and that's going to give us the square root of 2 squared plus 5 squared, which is going to be 29. So that's going to be square root of, this will cooperate here, 29. All right, that's the idea. So to find a vector in component form, we're going to subtract the x's. To find the magnitude, we're going to use the distance formula. Okay, so here's our 2 formulas that will give us the component form of the vector and the magnitude. We got a special vector that sometimes we'll use called the 0 vector. That's 0, 0. It just has no magnitude and no direction, but it is a 0 vector, and it has to exist to make some things work. Now we're going to use vectors and scalars to do what we call vector operations. And this opens up a whole world, a whole different type of mathematics called linear algebra. And lots of stuff that can be used with linear algebra. Lots of applications there if you continue on studying mathematics in college. So scalar multiplication is our first operation. And a scalar, remember, is just a regular good old number and a real number. And a vector is a 2-part number. And if we want to multiply a scalar times a vector, we have a times vector v. All that means is we're going to multiply the first component and the second component. All right? If we want to add vectors, add u, which has the components u1 and u2. Add vector v to that, which is components v1, v2. We're just going to add the first component and the second component. Basically, we're adding the x coordinates and the y coordinates. And we call this the resultant. Real useful and important number for us is that resultant there. All right? So that's going to be the resultant vector. So let's try that out. So we have a vector -2, 3 and a vector 2, 1. All right, and let's plot those on the top axis here. So negative 2, 3 is going to put us up here, and that's going to give us this vector here. Okay, and then we have 2, 1, right 2, up 1. That's this vector here. All right, and when we plot these on the top axis, we got two vectors going different directions. They got different lengths. All right. Now let's try to find what 2u is. Well, 2u, as we said from up above, 2u means we're going to take 2 times the component form of u. The component form of u is negative 2, 3. And we're just going to multiply that out. That's going to be 2 times negative 2 is negative 4. And 2 times 3 is 6. Kind of a distribution thing. So if we go negative 4 and 6, we're going to be up here. Okay. Now let's get that vector here. Well, that vector is going to look something like this. Almost. Okay. So there it is. Notice it's going in the same direction, and it is just doubled. We go over and up, over and up. Okay. It's just twice as long. So when we multiply there by a scalar, it just changes the magnitude, the length of the vector, but it doesn't really change the direction. Okay, so we get a new vector that's twice as long. That's the idea. All right. So now what happens if, now let's bring this back. What happens if we have a negative v? All right, well, negative v, it just means we have negative 1 times v, and v is 2, 1. So multiplying negative 1 times that gives us negative 2, negative 1. So what happens there? Well, we're going left 2, down 1. There's that. And now we're going to get a new vector going this way. Okay, so there's negative v. So we have v here and negative v. What happens? Well, that negative just changes direction. All right? Now we've plotted u and v on the lower axis here. And now what we want to do is we want to find u plus v. Well, u plus v, and those are vectors. We're going to add the vectors. The vector u is negative 2, 3, plus vector v is 2, 1. And we're going to add those, and that's just going to give us, I'll write it out here, negative 2, negative 2 plus 2, and 3 plus 1, and that's going to give us 0, 4. So that is what we call a resultant vector. 0, 4 is right up here. So that's going to be the terminal side of our vector. And so let's graph that. That goes right here. Now, we notice what's going on. We can check this out graphically. Graphically, notice here we're going over 2 and up 1. Okay? And so what's happening here is we have u here. And if we start at the head of u, we'll call this arrow the head and the initial side the tail sometimes. If we go right 2 and up 1, we copy this vector, vector u. Okay, let's copy that. These two vectors here, this one right there and this one right there, they're the same vectors. So we just move this vector up here. We can add them graphically by taking and putting one, the tail of one, on the head of the other one. Okay, so if we connect the vectors, we get those two there, and we get this one right here. That is u plus v. Okay, one more. If we do this, v plus negative v, notice we have negative v here. So v plus negative v or negative 1v. That gives us 2, 1 plus negative 2 and negative 1. And if we add those, 2 plus negative 2 is 0, and 1 plus negative 1 is 0. So we get our 0 vector, which isn't going anywhere. It has no magnitude and no direction. So there's a little introduction to vectors and how we can use them, how we can add them, and how we can use them with multiplying and adding scalars and vectors.